So welcome everyone to the non-typical weekly Gardener Celebration of Mind social. Very briefly, a couple of months ago, the hat tile was discovered, the world's first aperiodic monotile, but there was a little bit of consternation among some in the community because in order to actually tile the plane with this thing, you need to use the hat, or this is looks like a shirt, the hat, and its mirror image. You can see because of the adornments here, one of these is flipped. These are Dave Richardson's tiles. And, according to the formal definition of the problem, the reflection is an isometry, just like a rotation is. It's no big deal. But the result has now been tightened. There's now a single tile, the Specter, that works with just rotation and translation, and you don't have to reflect it. So that's what we are here to talk about. And we've got, we're very pleased to have a number of speakers, including the two authors of the paper, Chaim Goodman-Strauss and Craig Kaplan, Robert Fethauer, Yoshi Araki. And I thought maybe we would begin with Chaim to fill us in a little bit more on exactly what the mathematical story is here.
Okay, so this is the hat tile and the hat tiling. And of course, this illustration shows a patch by the hat tile. And we can, with some care, tell that there really are two orientations there. And okay, that's great. The result for the hat tile, just to make sure everybody is on the same page, but if you're here, most likely you are, is that it's a single shape that we can extend. We can find patches that cover the entire plane. That is to say, we can tile the entire infinite plane without gaps or overlaps. And moreover, it can never tile. No tiling by this shape is periodic, which is astonishing. It's still astonishing. And all of us, I think, have probably been very interested in this problem, whether from a mathematical point of view or physical, or just simply as recreational mathematicians. And so we have a single tile here. And the question is, I guess, a quibble or controversy, is this a single tile? And I would just like to cite a couple of authorities. So first of all, in the tiling community, sure, we should give credence to the counterpoint of view, right? I mean, the shoes come in two flavors, and three-dimensional objects really are different. The biochemistry of life very much depends on its handedness, but in the plane, we might flip things over. And I think that this beautiful illustration by Yoshi illustrates, makes the point pretty clear. I mean, how many different kinds of turtle design are there here? There's one kind of turtle design here. For sure, there's only one kind of turtle design. It's so hard to find the flipped over ones, and that's kind of cool, the puzzle. But if you didn't like that, I was recently teaching Euclid to some high school teachers, and I was reminded that in book 1, proposition 4, we can cite Euclid himself as an authority. And if you don't, so this is the side theorem. And if this isn't authoritative enough, then let's just do it in the original Greek. So we have some long-standing claim to this. Let me just explain what the point of this is. So this is sort of a notorious proof. So I'd just like to show this. So here is basically the substance of Euclid's proof of prop 4, book 1, is that you have two triangles, and if they have the same, two of the sides are the same and the corresponding angle between them is the same, then they're congruent. He makes no reference whatsoever to whether or not you can flip it over. And in fact, in the proof, or what he means by equal for that matter, but it's clear he means equal lengths and equal angles. And if in the proof, it's literally, the proof is superimpose the triangles so that the corner matches, the angle matches, and the two legs match, and then therefore everything else matches. Whether or not that's a proof is not clear, because Euclid himself never uses this principle again. But nonetheless, it's pretty clear that. So I think we can really feel that may seem a little defensive even to care about it, but you know what? We got a lot of stuff about it. So anyway, remember that the hat had this hierarchical construction that we were able to enforce matching rules. Basically, they force this hierarchical structure to appear, these shapes to appear, and then these shapes to appear into larger copies of themselves ad infinitum. And so this was a sketch from the original paper that Craig drew of the inflation. But then also remember that there was this wonderful new component of the proof, which is really even maybe as exciting as the existence of a monotile itself, is that on the basis of this movie, the movie itself is provides a new and distinctive proof of the aperiodicity of the tile. I won't go into that again, but I just want to remind you of what it is. So any moment in this movie, there's essentially two lengths that can be changed independently. And when they're changed, the combinatorics of the tiling doesn't change. So any one of these is itself an aperiodic monotile in just the same way the hat was, with only a few exceptions. So one is when one of the edge lengths vanishes entirely, there's more combinatorial possibilities now, and this tile clearly can also admit periodic tilings. And then the other end, when the other length disappears to nothing, we again get a sort of a degenerate case where this also can tile periodic. It can do this, but it can also tile periodically. But what we didn't notice, and we were really kind of frankly worried that somebody like here might notice, honestly. So kudos to you all for not noticing, I guess, is that right here in the middle, when we have this equilateral shape, which Yoshi was calling the turtle, this shape here actually also admits periodic tilings, because when you flip it over, you have just more possibilities now for how the edges can fit. So that's kind of the miracle. See, this tile has more combinatorics, and so now it has sort of a surfeit of combinatorial possibilities. And so just now by fiat, if we just simply did not allow reflections and only allowed rotations, perhaps there'd be enough structure there to still have something interesting. And so that's, of course, the insight that led to the Spectre. So here's a drawing of the Spectre. This is the same tile, this equilateral hat tile, if you will, now with the edges modified. Now that we allow only rotations, we can modify the edges in such a way to force us only to allow rotations, but also we have an infinite variety of possibilities now for how it works. And so I guess in just a few minutes, we're going to see some of these incredibly exciting possibilities. So I'm just going to quickly just sketch a little tiny bit about this and then turn it over to Craig, who will demonstrate this in a more vivid way. But basically, there's a cool little technical trick in the paper for that every tiling by these so-called these specters, where the tiles only are in one-handedness, you can deform to get. What I like about this is that you can deform it in such a way the edge length, you can change the edge length so that on the one hand you have a hexagonal grid with the hexagons facing this certain way, but then you can also deform it in such a way that the hexagonal grid is 30 degrees to that. And I think that's just kind of remarkable. I should also say what it is that we are claiming. So we're claiming that this is a chiral tile. We're claiming that this is a chiral aperiodic monotile, and many people have already commented that that doesn't make any sense in some real way. And the word chiral, and it doesn't. We're using the word chiral. Being mathematicians, as Humpty Dumpty said, when I use a word, it's how we choose to use it, or paraphrasing Humpty Dumpty in Alice Through the Looking Glass. And or was it in Alice in Wonderland? Sorry. So the word chiral means handed, like chiral molecules come in either a left hand or a right hand. And in that sense, the hat tile was chiral because the hat tile certainly had a right and left-handed. Well, no, it wasn't. We were claiming it wasn't chiral, was it? But either way, maybe it has a left-handed or right-handed. What we mean here is specifically that in a tile, that the tilings are chiral in the sense, in a very rigid sense, that the tilings all have one-handedness or another-handedness of the tiles. That you could have, clearly, if you have a tiling with all right-handed tilings, you can also have the left-handed one. So we just simply mean by chiral, being chiral in this sense, that the tiles will all appear in one orientation or the other. And let me just conclude very quickly with a sketch of the idea. So the idea is that we have, I forgot to complete this slide, but on the left we have a cluster, and on the right we have a cluster, and in the standard kind of hierarchical method that Robert Berger innovated in the 60s, we have a substitution rule. On the left, we use this as a rule for the Spectre, and on the right, we use this as a substitution rule for this pair, which we call the mystic, which is a pair of two tiles as such. Anyway, and Oh, there it is. That's the slide I was hoping for. And so in this way, iterating this, we have these larger and larger patches. And by the way, one thing in the paper is to actually be concerned about whether or not these patches, does this rule actually well defined? Is there actually a meaningful sense in which we can take the limit of these patches and not have somehow things overlap or collide? And I hope that that's a standard that future papers in this direction will adhere to. So this is a larger and larger cluster. And in the standard way, we go about proving that these work. So the first thing is that these clusters come in various flavors with various matching rules, which Joseph worked out. And then these are abstracted into hexagons. So now we have these combinatorial tilings by one, or any tiling by one is at least combinatorially equivalent to a tiling by the other. And then in turn, the substitution rules on the hexagons can be interpreted. The substitution rules on specters can be now interpreted as substitution rules on hexagons. And just to wrap this up, finally, we see that the original tiles themselves are these marked hexagons. And so in effect, but when all is said and done, we have this is the substitution system, complete with rules and complete with everything. This is not clearly a monotile. This is 9 marked tiles that you can prove in sort of by standard techniques that these 9 marked tiles must enforce this particular substitution system on themselves. But then the miracle really would be that all 9 of these have the same shape, and that, you know, there's one shape that does all of this. And with that, let me just turn this over to Craig and so he can show you how these amazing pictures are made.
I guess I could say a little bit more about drawing specters. Hello from a nondescript hotel room in Winnipeg, Manitoba, where I am for the next few days. So I was traveling yesterday. I threw together some very quick slides. Let me see if I can grab them. This is the content of the appendix of the paper. One funny aspect of this paper is that almost all of it is very combinatoric in nature. It's like, here's the proof that this stuff is aperiodic, and here's how we know that they tile the plane. But we don't actually tell you how to build the tiling. We just say these rules imply that the tiling exists, not where the actual tiles go. So it was useful to have an algorithm at the end that says, well, if you wanted to have tiles, where do you put them? So here's a quick overview of that algorithm with some hastily constructed slides. Like literally, I saved this file at 11 a.m., at noon, 11 a.m. Winnipeg time. We'll start with a copy of one tile 1-1. And of course, tiling chirally, as Chaim said, with this shape is equivalent to tiling with any modified edges you care to construct. So it suffices, of course, to show you the algorithm on this shape. So we start with tile 1-1. I'm going to endow the tile with 4 things that I call key points arbitrarily. I will join the points with a quadrilateral. The quadrilateral does not matter at all. It's just to make everything easier to see. It has nothing to do with the algorithm. But the important thing is I got these 4 marked points, and they are vertices of this polygon. And now I also need a mystic, as Chaim said. So my mystic will be identical to the tile 1-1, but it just carries along an extra copy of the tile rotated 30 degrees, just goes everywhere that the mystic does. All right, now to construct a cluster of this tile related to the clusters that Chaim just showed you, I'll just start by placing a tile that is reflected anywhere I want, doesn't matter. Just put it down in the plane, any position, any orientation. And now I will take another copy rotated by 60 degrees, and I will translate that copy so that those 2 key points are brought into a coincidence. So somewhere off to the side, I have a rule that says tile 2 is tile 1 rotated by 60 degrees and translated so that its key point number 1 is brought into coincidence with tile 1's key point number 3, right? There's a rule that's like rotation amount, key point, and that defines the transformation that brings the tiles to the right place. Right. And you just keep doing that. You write down a sequence of rules that look like this, and you just read the numbers associated with those rules off of this diagram, or if you prefer, out of the source code. Yeah.
I've neglected to mention, and so you should, that, or we should, that the rule, the substitution rule flips the tiles over, and therefore.
Oh yeah, that's so yeah. As I did say, this first copy is a reflected copy of the initial tile 1-1, and in fact, all the copies are reflected. And that, to me, that strikes me as utterly bizarre. We did discuss in the mailing list whether there are well-known substitution systems in which the rules flip everything over each time, and this one does that, which I find unusual. That's right. And then you just complete the patch by putting in a mystic as well. Same idea, same kinds of rules, but now we at last have a Specter cluster, as I call it in the appendix, I think. Then you just need to propagate key points from the initial tiles over to the clusters. Well, that's no problem, as it turns out. I identify, like, the first tile's key point number 1, and then 2, 3, the fourth tile's key point number 2, and so on. And those 4 points become the key points of the cluster. Then I just need to construct a comparable cluster to be associated with the mystic. And I do that just by deleting one tile. And now I've got a complete mystic cluster and a complete Specter cluster. And what's cool about this, of course, is that the exact same algorithm applies to these as applies to the tiles themselves. So I can build let's call it a Specter supercluster by assembling copies of the Specter cluster using the identical rules. So, right, the same key points define the translations, and I use the same relative orientations of clusters and complete with a mystic cluster to get a Specter supercluster with these key points identified on it. And I build a comparable mystic supercluster. And now I have my 2 superclusters, and I do the same thing again and again and again as many times as I want. The other cool thing I wanted to mention about this, and this is not in the paper, but it is in the source code for any hackers who want to look at the JavaScript code that does this. The same construction works fine with the other ways that you can visualize this tiling. So you can visualize it with copies of tile 1-1, or you can visualize it on these marked hexagons from the paper directly, or you can visualize it on tilings made out of hats and turtles, or turtles and hats. For any poker players, I think of those as hats full of turtles and turtles full of hats, but we don't, that's just a poker reference. And it's quite simple. You just you start with the 0 level tiles marked with key points, and here for the hexes, you just use these key points, and you just stick those into the exact same algorithm, and the algorithm blindly assembles clusters and identifies new key points, and it just works the same way. It kind of has to. The rules are very combinatoric in the paper, but geometrically it has to work out if you pass in other things like this. And the same works with hats and turtles. It works with turtles and hats. I don't have a demonstration of that except the live software. So let me switch to that.
While you're switching that, maybe I should make a pitch for why this is particularly interesting. So the examples of substitution tilings that we've had to date are all where there's a strict similarity from the tiles to the super tiles ad infinitum. And so here we have these combinatorial rules, and it's just an important technical question as much as anything. How do you make these patches? That's what is being, just so you understand what Craig is addressing. And to me, this is really exciting and really going to be helpful in a lot of projects.
And in fact, I mean, something similar happens with the hats. The hat needed comparable kind of combinatorial rules that execute a little bit differently at each level in code. But it works out fine. And I think you had a slide. Maybe you're taking over again after Chaim. He had a slide that he'll show you after. Oh, you're not going to? We released an updated version of the hat paper that has an updated figure 2.11, which refer to these H7, H8 clusters. We've jiggered that a little bit to make it look more like the substitution rules in the Spectre paper, starting with single tiles. Well, a tile and a cluster of 2 tiles. And those are kind of, they back those rules up one more step to start with individual tiles. It's a more natural starting point for thinking about those rules. So let me, okay, I'm sharing this now. Excellent. So you can go, there's a URL up at the top that hopefully you can see, or that you've already seen. You can go here to find out more, more resources associated with Specters. But the thing I wanted to show you in particular is the interactive tool. So in case you haven't seen it yet, I mean, there's really only one thing you can do. You can build larger patches from smaller patches, and you can visualize the different categories of patch that are in the paper associated with the different marked hexagons and so on. And they all look the same up to coloring, except for gamma, which is always missing one tile. And if you can iterate this as many times as you want. And as with the comparable code for hats, you can export images or vector graphics. So that's handy if you want to play with this. You get these really nice colorings too. This is a coloring scheme I added yesterday. These are pride flag colors, but you can go back and like just highlight the mystics if you want, of course, or the coloring that's used in the paper, or an earlier coloring that we experimented with. We found, by the way, that by coloring these differently, like for example, picking a subset and giving it one color and giving a different subset another color, you can really bring out all kinds of interesting filigrees and kind of fractal looking patterns in these tilings, which I encourage you to do because it may reveal other structures that we're not seeing yet. So the other thing that's worth showing is that you can also repeat this process with the Specters themselves. Whoops, build super tiles. This is just a sample Spectre that has curved edges. I did not build in the ability to edit these curves. I hope somebody does. Yoshi may already have a tool that does that. I'm not sure. And you can do this directly on the hexagons, which is pretty cool. And here you just get colors because, of course, it's just hexagons, but it's interesting to look at. Like what's interesting here, I will point out, here's some large, let's switch to the delta cluster. Here's some large cluster associated with the delta marked hexagon in the paper. If I switch to like theta, look at what changes. Almost nothing. I don't know if you even saw that, right? Just a tiny bit of information around the outside of the tile changes. So these rules, I don't quite understand what they're doing, but they're really just cooperating to put a tiny bit of variation on the outer edge of the tile, these corners. It's kind of neat. Anything else I need to show here? Oh, and of course we can visualize like, you can visualize this in terms of hats and turtles. It's very strongly equivalent to a tiling by Specters, but just with edge lengths changed.
Yes, there was interest in you expanding on the decision not to go with the name Mystic instead of Buddha.
Oh, okay. So can I can do that now if you want. Yeah. So somebody said, oh, hey, it looks like somebody in the chat today said it looks kind of like a Buddha. And that was like the first thing that I noticed when I put those two shapes together. First thing that pops out, it looks like a Theravada Buddha in seated meditation. Awesome. So for most of the lifetime of our working draft, we had called the shape a Buddha, but I was a little bit, I had some misgivings about that. Certainly, like, there are some religions for which that would be a bad idea. Like if I said, oh, it looks like the Prophet Muhammad, that is a very, very bad idea. I was a little bit less clear on whether it would be bad to call a shape a Buddha, because, a lot of Buddhists take a sort of semi-ironic view of the Buddha, and most certainly a lot of Buddhists do not view the Buddha as a deity in any case. I mean, we're getting into the comparative religion aspect of the talk here. In any case, I reached out to a professor at the University of Waterloo who teaches Buddhism, who is an expert on mindfulness and Buddhism. And after a conversation with him, we decided, like, yeah, you might not want to actually call it a Buddha. There are many Buddhists who object to the kind of informal use of the Buddha as like almost clip art. Like you go to a restaurant and you see a Buddha statue in the bathroom like that. It's considered a little bit insulting, right? Like, that's nothing to do with you. Why do you have that there? And in particular, we were concerned that if we called it a Buddha and somebody on the internet made like a puzzle or a t-shirt or whatever and started saying, buy my Buddha puzzle, That would be bad. So the compromise in the end was to say, we call it a mystic because it looks like a Buddha, right? That way, if people use the name defined in the paper, hopefully they'll call it a mystic, but we can think of it as resembling a Buddha. Hopefully that's a reasonable compromise. If you put out a puzzle or something, don't say we call this the Buddha. Thank you.
Thank you, Craig. That makes sense.
Yeah. Anything else?
Here, I can show that slide you were just talking about, though, just so people know what you were.
Yeah,
I'll just take
yeah.
the presentation for this
I'll
one
stop.
moment. This was in the original paper, and it didn't. Its relevance wasn't clear, but now I think we can ask, what about this substitution system on the original hat? Does it, for example? Oh, I guess it is enforced. So the hat itself has the same issue where, I guess, right? I think we can go ahead and make that claim that the hat has a very similar kind of substitution structure that it also enforces in a direct manner in the same way without additional markings or adornment. But that proof has not been done. I guess it's fair game for everybody to check it out.
They're definitely not the same rules. So you could it's reasonable to be surprised that there are comparable rules at all. I mean, it's not the same tiling, right? And yet we have these similar looking rules. Maybe that should be surprising. I'm not sure.
Hey, thank you, Chaim and Craig. And why don't we move on to Yoshi Araki? I believe you have prepared some slides.
So my background is one of the Spectre. You see, two-headed peak. Yeah. So the Spectre is very interesting because the boundary can be deformed, right? So I will show you some more stuff. So again, this is Yoshi from Japan. I'm a president of Japan Tessellation Design Association. And this is my turtle last time. And in this tiling, we have a reflected turtle, but thank you for the acknowledgement, and it's very honor to have my name in the paper. And this is a new version of the turtle. Now, all the segment, all the boundaries are curved, right? So no more reflected. By the way, I'm a left-handed person. Anyway, so this is I redraw just after I read the new paper of so this is the next picture I draw. So it is very new to me, the word Spectre. So what kind of animal should be. So I try to modify the boundary as much weird as possible, and I get a very good boundary with like this. In other sides, I want to make a much more cute stuff. So I have my dog, a white dog, and I draw the dog. This dog say, "Oh, I want to paw," right? So any more initialization, and we can utilize the tools. The friend of mine, aperiodic, he made tools for that. I can show you. Okay. So Desmos is tools. Actually, this is for some mathematical education. Here is a control point you can easily modify. So there are 4 control points here, and you can change the curve if you want, And actually, so bunch of shape you can make. You see. So imagine you can make a spiral like this. You see. You can get a much larger stuff. Okay. So this is very good for you to start to familiar with the spectral shape and let's try tinkering stuff. Okay. What you can find with the tools, it might be spiral, but sometimes it will be difficult for you so during my change the curve, I saw eye to eye with him. So who is him? Maybe it's like a monster or something like that, right? So I get him. Okay, you see, he has hands. It may be dangerous or not cute, right? So sometimes you see some more other animals. So someone said how to find them, but it's not me, but each of them to find me. So I guess the eyes and I contacted and they find me actually. My nephew said this is a stegosaurus, right? You can see. So this is very fantastic experience for me. So you see, this is some kind of elephant. So you can try the same things using these tools and please post your own finding. This is some kind of weird stuff and maybe much more thin edges or something like that, but it's still single connected region or something like that. So other stuff, my concern is a large scale structure. Your tool is very good for coloring, so we can find a much more important, feature from the large structure, right? So this is my recent drawing. This is a hot tile, but I can convert to this might be helpful to understand the structure also. Yeah, thank you for your hearing me. Thank you.
Thank you, Yoshi. That's wonderful.
I will paste a link to the tools.
Thank you. We do have more people who have prepared something to speak. Robert, do you have anything to say today?
Not much, a little bit, I guess. Yeah, literally just spent like 2 hours playing with this, and all I did was one simple modification of the edge. When I saw it was called I think you can see my sharing screen, correct? When I saw it was called a Specter, I thought I should make a ghost tile. And in America, anyway, the most famous cartoon ghost is probably Casper the Friendly Ghost. So this is kind of the whimsical Casper the Friendly Ghost tiling. That's really all I did. The other question people might have is whether I'm going to make a puzzle, produce a puzzle. I would say probably not. I still have most of the hat puzzle, which I made as shirts. Yeah, this is a funny situation. I think because the hat tile got so much press, this one probably won't get nearly as much press. And so it's be interesting in the long term to see how famous the two tiles are relatively. I don't know if there's enough press to sell very many Spectre puzzles. Anyway, I do have a lot of hat puzzles, so if people want those, and you guys should have waited a while so I could sell more before you one-upped it, but anyway.
I'd just like to say this is what I saw when the first version of the shape that I saw exactly this Casper, this form. So I'm really glad that you drew this.
Yeah, it seemed an obvious thing to do with it. I have not really played around the modifying edges like Yoshi has.
It's that head. It's the head shape there. It's just got that little kind of weird cap.
That's about all I have to say, unless someone has a question. I had a question for the math types here. Is there any, I mean, in the hat tiling, you get this interesting appearance of the golden mean. Is there any special number that comes up anywhere in the Spectre tiling?
Yeah. I don't know the number. It's the coordinates in there again.
Yeah, you could do the same calculations, but they don't seem as closely connected to the golden mean. So the inflation, the areas inflate by a factor of 4 plus the square root of 15. And then the number of people want to know, you can label specters as even or odd because there's a sparse subset that are rotated by 30 degrees with respect to all the others. And those kind of play the role of reflected hats, right? They're the oddballs. We were calling them the oddballs for a while. And the ratio of oddballs to not oddballs is 1/4 plus the square root of 15. I'm sure you can construct that out of the golden ratio if you want. But,
Thank you. Peter, if you are still here and are ready, then you're welcome to jump in.
Yes, I think this is all rather marvelous, and I look forward to going over the papers. I discussed this problem with John Conway quite a long time ago, and he said he had absolutely no idea whether or not there was a single monotile that tiled the plane aperiodically, and he had absolutely no idea of how you might attack the problem. So I think it's really shows tremendous progress in our understanding, and also technology has a role here because we can make these tiles by laser cutting and whatnot and experiment with them. I think that that's a wonderful development. So suppose there's a tiling where no two tiles have exactly the same orientation. And also I have a comment about this. You used to say the tile is rotated 30 degrees. Well, that suggests that you mean that you have a chiral plane. You have a plane in which you know the difference between a clockwise and counterclockwise rotation. Or does it make any difference? That's the question.
You just set your framing and decide that's the one you are measuring against. So similarly, 30 degrees relative.
Well, so as soon as you put it down, you've oriented the plane.
That's right. And then all subsequent tiles will be oriented the same and at 30 degrees.
I was glossing over. Yeah, I mean, I meant something a little bit more precise than just rotated by 30 degrees. But if you give me any drawing of a tiling by Specters, I can tell you which ones are the oddballs without any trouble.
Because they're sparse or sprinkled in a certain way, correct? I mean, there's a geometric way of distinguishing.
Sure, yeah, there's like a combinatorial way because their neighborhoods look different from the neighborhoods of the other tiles. But you can also just like assign an orientation to each tile, regardless of how you've rotated the whole thing. And those orientations will be one of 12 possibilities. And there's going to be a sparse subset of 6 and a less sparse subset of 6. And the sparse subset are the oddballs, right? There's, if you give of all infinitely many tiles, there will be 1/4 plus the square root of 15 of them that belong to 6 less frequent orientations versus the other 6. And those I can tell you are the oddballs.
If you know the tiling in the neighborhood of infinity, that determines the tiling in the whole plane or not?
We don't know, but probably.
Yeah, that's...
Because the thing is, this one has a feature, because of all those markings are substituted on, there's sort of a related question of, are there, like the Penrose tiles, there's no, well, there are worms, but there's not really any way to slide super tiles past each other like you can in the Robinson tilings, if you're familiar with those. And the hat tile, it turns out that you can kind of flip the super tiles around. And I haven't really investigated this, and I don't know that any of us have, but I am expecting that that the super tiles will be much more rigid with respect to each other because of the way these markings are inflating. And if that's the case, which may not be, then the neighborhood of infinity would certainly determine everything, but not known.
Interesting question.
But I have just another thing that's sort of striking to me is that the odd specters, so to speak, that Craig was talking about, You know, I think when you look at the pictures, they clearly have sort of a similar role to the reflected hats. What is it? Can anybody explain it? Does anybody have a coherent, you know, message about that? Besides just, it may end up just being, well, that's the way it is, folks, which is, you know, that's just as good a reason as anything. But it is really striking that there's, you know, these 1 in 7 or something oddballs, 1 in 10 oddballs.
Arthur points out that, well, at least this is true, Arthur, for tile 1-1. It's not true for specters with modified edges. But if you have a chiral tiling by tile 1-1, you can always flip mystics over because they have bilateral symmetry.
That's true.
So at least for straight edges, you get like an explosion of distinct, combinatorially distinct tilings.
Well, including periodic ones, you know.
And I don't remember the timing on this, so it may not have come up at a G4G meeting. Going back to the hats for a second, did you say this already, Chaim? People have found small, finite patches of hats that can be, or finite regions of the plane that can be tiled by hats in more than one way. The smallest one I've seen is made out of just 6 hats. So that's interesting. I mean, maybe that applies to specters as well.
But those can't be extended, right?
Yeah, not necessarily. That's probably not. You're right. Still thought it was interesting. This is particularly of interest to like anybody who's designing a puzzle of hats, right? Like to fit in a little tray. Now there's more than one solution.
Oh, you know, could we have Dave? Dave, are you here? Would you like to? Could we invite Dave to say something?
I just wanted to say that I really want to thank you guys, my team, for the whole thing. I've never really had a chance to say it on air, and especially at the end of this one, because I became quite nervous and I was worried that someone else might get there before us, and that would have spoilt the whole thing for me. I would have been miserable for weeks probably. So I really want to thank you guys. So
Rex, you're thanking the people here that didn't figure it out more than you're thanking us.
Well,
so thank you for not figuring it out, folks. I agree 100% because we were worried specifically about some of the people here, to be frank. So
that's right. Yeah. I'm just surprised nobody noticed it, or maybe they did. I've just really popped in just to have a listen. Just to say hello.
Thank you, Dave. Thanks for joining us, and
Dave, for setting all of this off. I mean, clearly we're all just astonishingly grateful to you for pursuing this and searching over this. This was a big haystack, to find 2 needles, or so to speak. Nobody, it's way more than we could have expected.
I have a question, and someone just put this in the chat actually. Are there any versions that aren't curved at all? Someone put a link to a picture, but I don't know it.
Yeah, this is something that deserves to be explained in a little bit more detail. The paper talks about curves on the edges because that's the easiest way to guarantee that you can never be adjacent to your mirror reflection. But probably in practice, most things that you can do to those edges will work the same. We just didn't want to take the risk that, oh, there's some magic polygon that just happens to like introduce additional adjacencies. So probably just about any polygonal path you can put between edges will work too. And we experimented with some. We just, for the paper, we didn't want to like go through this huge effort, what would probably be very complicated, to try to characterize all paths that worked. But go ahead, Chaim.
But I just, I put this up just to point out, I mean, there's no constraint that it couldn't be polygonal. I mean, you can make these polygonal just as easily. It's just, I mean, my feeling is they look cool, they're curved. But of course you have to do something, because if you don't do anything at all, the original 1-1 tile, this original tile can be flipped over. So That's all. You just have to modify it in some way, unless you just sort of say you can't flip it over. So by the way, I guess for ceramics and stuff like that, people were pointing out that the ceramic, if you're going to actually tile your bathroom, it really does matter. You will manufacture these differently than
More.
one way or the other, but you won't have to do that with this guy. And so if you don't do this with this guy, you can actually use let's see, I don't seem to have one. You can actually use an equilateral Spectre in your bathroom because you'll have the glazing. So, the polygonal equilateral Spectre. But other than that, if you really could flip it over, you do need something, but you can still do it with polygons, just more complicated. I have to say, I'm so excited to see what everybody's coming up with and all the stuff. And again, I was asking you individually, but I'm trying to collect stuff. I intend to write a survey of just how the cultural, it's just so exciting to see all the different ways that people have made it their own. It's what could be more rewarding and interesting and gratifying. So please do send me your stuff. I would like to just have a place that I'm collecting it. And so I'd like to know that anybody is collecting it, really. And again, we will have this hat design contest where we, that we'll announce formally in the summer and then throughout the fall. And everything that we've seen, is absolutely right. Well, we're inspired by everything that we've seen to have the contest. So
Thank you. I did want to give Dave Richardson a chance to chime in. I believe he had some material prepared. If you're still here, Dave.
I'm here. Yep. First of all, to congratulate and thank the authors, discoverers of these tiles. It's been fun to watch and fun to play with. I just wanted to let you all know that I made 3D printable versions of these tiles, which you can find on the Thingiverse website. I have a slide at the end that has all the links, and I'll also put it in the chat. So I guess working backwards chronologically, there's the polygonal Specter tile. I made one with the curved edges. These are just semicircles, either going in or going out at each edge. The picture on the right shows the polygonal one with the curved one sitting on top of each other, so you can see how they're related. It's not obvious to me if I just hold them up, but when they're sitting on top of each other, you can see. And then if you want to go old school, I did also have a page with the hat tiles that you can print and the turtle tiles that you can print. And then 2 or 3 days ago, someone on Twitter asked if there were like coloring book pages so you could color your own. So hopefully later this afternoon, I just made these and was going to put them on my blog so that people can download and print them. So thank you again for all this exciting work. It's been amazing.
Thank you, Dave. At the very beginning, these are some of Dave's pattern tiles, which are very cool. You stick them together and get the curves connect in interesting ways.
there were some people asking about the name, and I don't feel qualified to answer it. Perhaps you are, Craig. Why is it called a Specter?
I mean, the reason is simple and is both due to Dave and in deference to Dave. He just said early on, can we please call this the Specter? And having recklessly and apparently controversially suggested that we go with hat for the first tile, I was only too happy to say whatever you want. And of course, it is kind of a cool name. I don't think it has to have a very specific meaning. I like the name, but it's all due to Dave, and I think he fully deserves the privilege of choosing whatever name he wants.
Dave, are you here? Can you confirm that?
Yeah.
I have the email.
Yeah, I thought about the Mysterion as well. But I don't know, I just thought it was some sort of spook or being, you know, that's what I saw. And I liked that. So it stayed.
Personally, I'm waiting for the memes that are mixing up the Bond movies and the Spectre tiles.
But I created a poster. I did that. I modified a Spectre poster that I sent to my co-authors. Yeah, of course.
Well, someone in the chat also mentioned the idea of it being a Spectre because it has no reflections. I don't know who
Well,
did that, but I like that.
That's brilliant.
That's why I suggested vampire.
Thank you again to all of our presenters. This is, you've blown our minds one more time. And any final questions or remarks by anyone before we stop the recording?
I haven't done anything interesting mathematically with the tile, but I guess my job here is just to kind of shout about it from the rooftops, which, you know, give it the respect it deserves. And so I've had an interesting experience in kind of bringing it to TikTok. And I can tell you that I got loads of amazing comments from the first one, the hat. Everyone very, very much arguing about the fact that it should be called the t-shirt. And there was a huge debate that broke out between potters and pavers as to whether you can flip the tile over or not. So everyone kind of really took issue with it being called a single tile when it was flipped over. So when I signed up for doing kind of maths communication, I did not think I would be beholden to such a quick news cycle as to then 10 weeks later having to put out another video. But I can tell you that the new shape has been much more appreciated on TikTok. Everyone is happy, very, very happy that it does not involve the reflections. A lot of people enjoy the vampire pun and the Spectre name. And the thing that everyone is taking issue with now, which I thought was going to be an offhand comment, was the fact that it's a 14-sided polygon. It's just that 2 of the sides are collinear. So that's my current argument that I'm having in the comments section in TikTok, if you want to know what's going on in that world.
They can just call it a 13-sided gun and be happy. But tell me, were both the potters and the pavers against it, or was there a division of opinion? The potters took one side and the pavers another.
Yeah, the potters were, they want to glaze one side. So they're very much, if it's a tile, we need to decide which way round it was. The pavers were like, we don't care. We will flip it over. We will get it on a pavement.
Oh, interesting. I would have thought the pavement would also have a side.
Thank you again to everyone. And it's been a real pleasure. And I will see you at the next Gartner event. Bye-bye.